All right, so we are drawing out this particular molecule again. Okay. And so remember that I said that you can kind of go backwards. Once you know the Lewis structure, you can sort of work your way back to the hybrid orbital diagram from here, right? Because if we know the Lewis structure, we can predict the hybridization state, we can predict all of that from there, right? So let's look at the hybridization states of all of these different carbons. What's the hybridization state of this carbon right here?
SP2.
Because there are 3 electron groups around that. So that's sp2. Okay, what about this one in the middle?
SP.
That's right? 2 electron groups, sp, and then this is just the same as the one on the right, so we're going to call that sp2. So let's focus on that sp, that middle carbon, and let's try to understand how to put that on like an actual coordinates scale, right? So what I'm going to do first is I'm actually going to draw out, kind of sketch out a 3 x, y, and z coordinates, just so we can like have something to work with. And it doesn't matter where you label. Let's just say that's z, that's x, and that's y. It doesn't really matter. Just pick any 3 coordinates. Okay, I'm going to put this carbon right in the middle. And this is very reminiscent of what we did in class with these sp hybridized carbons. So we can actually take that model and come bring it back here. So an sp hybridized carbon actually means that there are 2 sp orbitals that are 180 degrees from each other. Right? That's like how you're getting that linear geometry in that particular molecule. Does that make sense? Okay. So then you have, let's just put that on the y-axis. Okay. So that's your sp, and that's your sp. But we also will have some unhybridized p orbitals in an sp hybridization state. And if you remember from class, how many unhybridized p orbitals will we have in an sp hybridization state of an atom?
2.
Exactly. And where would they be? Like, if we put this sp orbitals on the y-axis, where would the p orbitals be?
On the x-axis and the z-axis.
Wonderful. So there will be like 1 right here. So that's 1p. And then there'll be another one right here. Another p. Okay? So that's the picture for the middle carbon. So now what we're going to try to do is draw the picture out for the terminal carbons. So the ones on outside of that middle carbon. So I'm going to try to extend this thing a little bit, and I'm going to draw out another set of coordinates right here. Your x. Your y. Your z. Okay. So now, remember that a double bond is a sigma and a pi, right? Let's start with the pi. A pi bond is an overlap of p orbitals, like side-on overlap of p orbitals, right? Okay. Which p orbital do you want to engage in the overlap for the right carbon? Do you want the p on the z-axis, or do you want the p on the x-axis? You pick one.
On the z-axis.
Okay, let's pick the z. So if we pick that, you have now dictated the structure of this CH2. So you have a z-axis right here. That is where your pi bond is going to align and form with the PZ in the middle carbon, right? Because you have stated that you want to overlap that you fixed that pi bond. Does that make sense?
Mm-hmm.
Okay. Because you have those p orbitals right above, just top down, right on the plane of the board, that carbon is sp2 hybridized, right? How many sp2 orbitals are around that carbon?
Oh, 3.
Right. So you actually need 3 of those sp2 orbitals to be in that same geometry to actually make up
okay.
that. Yeah.
I got it.
So that's going to end up, you would have one here, right? Because that's going to overlap with the sp in the middle. The other 2, and you want to be careful about this, is going to be going in and out of the plane of the board. And let me draw it first, and we're going to explain why. So the other ones are going to be, I'm going to try to draw it in a way that it might make some sense. Oops, I should not put I'll put the hydrogens right now. They should be essentially flat this way. So if you're looking at my screen, I'm showing you, I'm like putting my hands in and out of the camera. And why is that the case? Well, that's because the p orbital has to be 90 degrees away from the sp2 or sp hybridized orbitals. The entire sigma framework needs to be 90 degrees from the p orbital. So what we mean by that is this angle right here is 90 degrees. This angle right here is 90 degrees. This angle right here is 90 degrees.
Okay.
Okay? All right. We've done one side. Let's do the other side. So, we're going to extend the diagram this way. And we're going to put another z-axis right here. And another x-axis right here. And we're going to then throw in that second carbon, or the carbon on the left. Okay. Where must the carbon on the left's p orbital reside in order to actually have a proper pi bond?
On the x-axis?
Yes, and why?
Because we put in the middle one, we put it on the z and the x. We already put it on the z, so we have to put it on the x now.
Bingo. Bingo. Okay, so the other one needs to be on the x-axis. So there you have that, and then you have that. Okay, so that's how you're going to form that pi bond. All right. You with me there? Okay, so that means that on the left, that p orbital is literally coming in and out of the board.
Okay.
So where must the sp2 orbitals be with respect to the p orbital?
90 degrees? Okay.
Thumbs up, thumbs up, thumbs up. So if it's the plane, if the p orbital is coming in and out, does it make sense that the sp2 orbitals will be like on the plane, like going this way? Yeah, that's exactly right. So you should have like, and just this is gonna get really gnarly, and I'm sorry. I'm sorry. So you can think about this drawings like that. If you just assume that those sp2 orbitals are literally twisted in such a way that they're diagonal but on the plane of the board, and then you have your third sp2 orbital right there. So sp2, 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 and then you have your hydrogen.
Okay.
Do you see where this is going? Yeah. Okay. All right. So we have formed our system, right? So we have our sigma. Oh, Leah, do you have a question?
Sorry, I don't want to interrupt, but just a quick clarification. When you put like the 3 sp2s, like say on the left carbon, is that because there's 3 electron groups?
Yes.
So you put 3 you put like the hybridization, you put 3 of them for that's equivalent to the number of electron groups.
Yes. Yes.
I don't know if that makes sense.
It does make sense.
Yeah, okay.
It does make sense.
Okay.
Yes.
Okay, thank you. 'Cause I was looking at the worksheet and I was like, wait, why am I putting 2 of these? But there's 2 electrons. Yeah, okay. Thank you.
No problem. Yeah. Okay. So, Jackie, just to like hone it down and just like wrap this one in a bow.
Mm-hmm.
So we know these hydrogens right here are on the plane of the board. Can we agree that they are like literally on the plane of the screen? Okay. So these two are on the plane of the board. And we know that because that's where how you project those sp2 orbitals. What about these ones? To the right. Where are they?
Are they like this?
Yes.
Okay, got it.
Yeah, so these are projected in and out of the plane of the board. So then, is this molecule flat?
No.
Right. It's not flat.
Yeah, no, okay, got it.
I know, organic. We're already It's like day 2, and it's like, what is this? But that's how, like, this is, once again, right? This is going back to Heidi's question about, like, why do we hybridize? Like, what is the meaning of this? Or even, like, I believe Charlene was asking a similar question about this, but it's an explanation of what we already observe. This molecule, we happen to know from experiments, is not flat. This molecule is not flat. And it happens to be that, like, and so the question is like, why, right? So we can explain that using hybrid orbital diagrams because of our understanding of orbital overlap and how that makes up bonds in